Okay, recall that we did this experiment with the red cart being pushed and then coming back, and we had this graph of position versus time for that red cart. We had 4 different segments of this graph that were each linear. And whenever we have a linear segment of a position graph, it means that the slope in that region is a constant value. We had a constant value of 0 meters per second here, a constant of 0.6912 meters per second here, a constant value in this region of negative 0.5067 meters per second, and then down here, if we sort of ignore that little blip, our slope in that region is a constant 0 meters per second. The slope of a position versus time graph is the velocity of the cart along the direction that the object is being measured in. So in our case, the x dimension in an xyz space. Our question in the previous video was, why does the velocity of this object ever change? So of course you saw my hand give the cart a push. So my hand is what initially changed the velocity from 0 meters per second to 0.6912 meters per second. Then the cart went off screen and we didn't see what happened to change its velocity to this different value of negative 0.5067 meters per second. But you can probably guess what happened. The cart hit something off screen and bounced back. And here we have an image of exactly what happened. So that's what I want to get into right now. An object's velocity will not change unless it interacts with some other object. And of course at the end of the experiment we saw that the velocity changed again because the cart interacted with the motion detector. So every time the cart interacted with a object, it resulted in a change of velocity. My hand, the bumper, and then the motion detector. The idea that an object will not change its velocity, it will not speed up or slow down or change its direction at all, is what we call inertia. And the law of inertia says that objects do not experience any delta V unless they interact with another object. We will actually clarify that in a little bit more detail in a future lesson. But right now we want to emphasize that delta V does not change unless the object is it's interacting with another object. When we talk about an object having mass, we're talking about it having inertia. Mass is a way to measure inertia. So that red cart has a mass of about 0.5 kilograms, which is about the same as a bottle of water. If you have a 500 milliliter bottle of water, that's a half kilogram. If I had a much more massive cart, like say 6 times more massive, I put a 3 kilogram cart there, that same amount of push from my hand would still give a more massive cart some change in velocity, but it would be less of a change than the 0.5 kilogram cart actually experienced. The more massive an object is, the more it resists a change in velocity. Again, we'll come back to this more in a later topic. The experiment with that red cart, instead of looking at a graph of position versus time, we could look at a graph of velocity versus time, which is what I went ahead and did. Okay, now that it's a velocity versus time graph, you can see that the velocity is now the vertical axis, still time on the x, or on the horizontal. And for the first second, I have a velocity of 0 meters per second. Then the velocity very suddenly becomes this value of about 0.7 meters per second. And according to the computer, the average value of the velocity in here is 0.6918 meters per second, which is what we had calculated the slope was on the position graph. So pretty close, almost the exact same value. That is the velocity during this time, and if you look at this graph, it's pretty constant with this little blip in the middle. Then off screen, the velocity very suddenly changes and becomes this approximately negative 0.5 meters per second. Again, the computer gives me an average value in this time. It says the average velocity in this period of time is negative 0.5067 meters per second. And then at the end of the experiment, it has this sudden change of velocity again, goes back to 0 meters per second. We will actually look at velocity graphs a lot more than position graphs in this course. And the reason why it might be more obvious in the next experiment. This experiment is the exact same equipment. We set up the motion detector and this cart, but I put it on a table and I tied a string to the cart, and on the other end of the string there's a little weight that falls like this. So the result for the cart is this. I'd like you to take a moment to think about what the graph of position versus time would look like for that experiment. Consider what the graph of velocity versus time would look like for that experiment. If you want to take a moment to pause this to make a prediction, then go ahead and do that. But we're going to go ahead. Here's what the graphs actually looked like. You can see that the position, it starts out around 0.35 meters per second, and the velocity is initially 0, which makes sense because the velocity is the slope of a position versus time graph, and the slope of this graph here is initially 0. But then the position starts getting more and more and more. As the cart goes farther and farther to the right, its position in the x direction gets more and more and more. But this doesn't look very linear. So my ability to take the slope of a nonlinear graph over here, that's a little tricky if you are not familiar with calculus. And this is a non-calculus course, so we're not going to try to use calculus. I will point out you could use algebra to make a line at a linear line segment there that just touches the curve at 1 second. And you could determine the slope of that one line segment. That would tell you the velocity at exactly 1 second. And then you could do the same thing at 2 seconds and do the same thing at 3 seconds. And if you did this in enough places, you would have a good enough data table of the slope at each of these positions that you would know what the velocity is at each of these positions. But that's just a roundabout way of saying that you could make this graph. Each of the data points on here represents what the slope is of this graph. And that's the whole point of calculus, really. If you've taken calculus, hopefully you already knew that. And if you haven't, then I just want to point out that that's the whole point of calculus, is to tie the slope of one graph to the shape of the other graph. Looking at just the graph of velocity versus time, I have a lot of information I can get from here. I can actually get a lot more information from this graph than I could from the position graph, especially if the velocity is not constant the whole time, but rather is constantly changing. I can determine the v initial, that's the velocity initial, that's what that represents right there. Initially, the velocity was 0 meters per second. I can determine that the velocity became 0.543 meters per second. I can't read that off that graph. That's too much detail. I hovered over it and it gave me that value. If you ever had to get these values off of a graph, I would give you more detail on the graph, a much cleaner picture. We'll take a look at it in the example problems, but don't stress about the level of precision, please. The average velocity I could determine by adding the initial and final velocities and dividing by 2. The average velocity is also the displacement divided by the time elapsed. That's how we defined it earlier. But I want to point out you can get the average velocity this way, just like if you took 2 tests and I said, what's your test average? You would know, oh, I add them together and divide by 2. This is how you can find the average velocity for a period of time. Add the initial and finals for that period of time and divide by 2. From this graph, I could also determine delta V, the change in velocity, while my cart was interacting with something. It was experiencing a delta V because it had that string pulling it. So how much delta V? I can find that out by reading the graph and finding V final minus V initial. Once I know delta V, I could find what delta T is for that same elapsed period of time. Delta V and delta T from here, say, to here. And I now have 2 data points on my graph that I could use to find a slope, a beginning and an end. The slope of this velocity graph is 0.2241 meters per second per second. We'll talk more about those units when we do some sample problems. The slope of a velocity versus time graph is a term that we call acceleration, and we want to make sure that we know that acceleration is calculated algebraically as delta V over delta T, but we also want to make sure that we're clear on the fact that the acceleration of an object is the slope of that object's velocity versus time graph. Okay, in our next video, we will do some introductory sample problems, and the videos for Wednesday will dig more deeply into these equations for acceleration and velocity and displacement and how they all relate to one another for more complex problems. So on Wednesday's videos, we will sort of reach our peak of kinematics problems for the study of motion in one dimension.